Hey there, welcome to another edition of Kung Fu Physics. We are working our way through practice physics GRE problems, and I have another mechanics problem tonight. I'm really exhausted, by the way, so if I seem a little off, I am a little off. And I'm hoping I can do this in one take or two takes and go to bed here, because I am exhausted. The one that we're going to do tonight is number 93. Number 93 off of the 1986 exam, right? Yeah. Number 3 of the 1986 exam. So let's go right into it. I usually scan the answers. There's a little bit of variation in the magnitudes of those answers. Just note that. Quick look at the diagram. Read the text of the problem. 93. An electric sander has a continuous belt that rubs against a wood surface as shown schematically above. The sander is 100% efficient and draws a current of 9 amperes from a 120 volt line. The belt speed is 10 meters per second. If the sander is pushing against the wood with a normal force of 100 newtons, the coefficient of friction is most nearly. So I can't help it when I see a problem like this. The first thing I think about is work and energy, and that's kind of how I got to the answer. I'm still not exactly totally happy with this problem. I mean, there's a couple things that I am not sure I would remember really well that I want to make sure I commit to memory, for example. But anyways, for starters, the thing that I want to know is what is the energy that's being generated by. I want to start with the sander and this energy that's coming out of the line as they describe it. Now I know that, and this is one of the equations that you should commit to memory. The power, electrical power, I'm sorry, I may have to grab another marker here. The electrical power is given by the current times the voltage. Okay, you should definitely commit that to memory. So the power is the current times the voltage. But that's not the energy, is it? Now I'd have to multiply the power times the time that current and voltage is delivering that power to the system to get my total energy. So this would be my energy. Now what's happening is this is electrical energy that is being generated over some arbitrary amount of time here, and it's converted into mechanical energy. It's turning the belt, and then you're having friction going on, and it's nice because it says that the sander is 100% efficient. I'd love a sander that's 100% efficient. Wouldn't that be nice? Anyways, it's converting it all into mechanical energy, and it's basically rubbing the sandpaper or whatever against the surface of the wood and converting that all, which is ultimately all going into heat energy, right? But before it does, I mean, all the work is there because it's 100% efficient. We don't have to think about that part of the problem at all. All of it is there. So the force, now how else do you know? I mean, if this is going to be our energy, well, we know that the total amount of work that a force is doing is going to be the force dot our distance, right? Our distance. Okay, so this is kind of the relation where I started with this problem. Power times time equals force times distance. In other words, I'm seeing that the energy is, of course, conserved. It's the same in any given amount of time. If I let the sander run for 5 seconds or 5 minutes or whatever, then eventually all of that is going to be used to do mechanical work, and eventually that'll all be converted to heat. But it's going to have the force of friction working over the distance that the belt has traveled, because the belt is sort of traveling the distance here. I don't know if it's sort of counterintuitive. It's counterintuitive because nothing's really moving. It's just going in a circle. The belt is going in a circle. But this is the way that I sort of see it, and it's maybe a little weird. So if it works for you, fine. If you got another way to do the problem, fine. But you're probably not looking at this video if you've got a better way to do the problem. So anyways, what you can do with this relation here, once you have, I don't know why it does not want to draw a T here, but power times time equals force times distance. Power then equals force times distance over time. Okay, so distance over time, in fact, that is going to be the distance that the belt has moved across the surface in an amount of time, which is also equivalent to the velocity that they gave us in the problem. So if I start making my substitutions here, what is my force? My force is the force of friction, and that is equal to the coefficient of friction multiplied by the normal force. My power, I've said, is equal to the current times the voltage. This is a big V here. And that's equal to my coefficient of friction times the normal force, that's F, times distance over time. And distance over time, this is going to be a small v, is the velocity. And I can just rearrange that. I get mu equals I times v, normal force times the velocity. And then I can start plugging numbers in here. I is 9 amps. Voltage is 120 volts. The normal force is 100 newtons. Everything looks to be in standard units. And then the velocity is 10 meters per second. So I get something like that. I can simplify it, drop that out. I get 9 times 12. If you're really good at math, you can just do that in your head. I'm not saying I'm really good at math, but I can do that one, I think. 108 over 100 equals 1.08. And we go and check the answers and see if we got an answer here. It's not exact. 1.08 is most nearly to answer D, though, 1.1. And I'd feel pretty comfortable being that close to it, rounding up a little, because it does say most nearly. It doesn't imply that it's exactly. Not that any of the physics GRE problems ever would. But, so yeah, that's sort of my work through on that one. As I said, I'm exhausted. I was actually trying to post another problem, and I can do the problem. Sometimes I can do these problems, but it's hard to come up with any type of meaningful commentary on it, if that makes any sense. And I just want to go a little bit deeper and get my understanding a little bit deeper before I post that problem. So this was kind of an alternate one that I had lying around that I decided I would do instead, because like I said, I'm exhausted. I'm going to turn this off, turn off the lights, and go to bed. So, as always, comments are welcome. This is one problem that I have to admit, it makes sense to me. It really does. But it seems like there could be something more to it. Maybe an easier way to do it, or something like that. I don't know. Comments are always welcome on these videos, of course. I do read them and look at them, so feel free. Anyways, that's number 93 off of the 1986 exam. Study hard, as always. Good luck.